Hello everyone. Today we are finishing our trigonometry unit with section 4 covering trigonometry in the coordinate plane. Before we get into the coordinate plane piece, which is example 1 here, we need to talk a little bit about a special relationship that you might have noticed between sine and cosine. So if we're looking at this triangle here, sine of A, sine is opposite over hypotenuse. The sine of angle A would then, for this triangle, be 7 over 25. So let's write that fraction down, 7 over 25. And then we have cosine of angle B, which is adjacent over hypotenuse. So we have the adjacent, which is 7, over the hypotenuse, which is 25. Oh, look at that. They're the same. And that's going to happen for any triangle in a certain situation. The sine of any acute angle is equal to the cosine of its complement. So complementary angles are two angles that add up to 90 degrees. So anytime you have a right triangle, the other two angles will be complementary. So in general, when it says how can we generalize this, what we're going to say is the sine of any acute angle is equal to the cosine of its complement. And that would be and vice versa as well. Meaning the cosine of any acute angle is equal to the sine of its complement. So it's the same thing. You can flip the sine and cosine around. All right. Now let's take a look at trigonometry in the coordinate plane. So example 1 here says find all side lengths and angles of the triangle with coordinates A at 1, 1, B at 3, 5, and C at 5, 4. So the first thing I'm going to do is plot those points. So I have A at the point 1, 1. I have B at the point 3, 5. And I have C at the point 5, 4. And now I'm going to connect those dots here. You might see it coming, but we are going to be working with a right triangle here. So B would be our right angle. My lines aren't perfectly straight, but that's all right. You can still tell. Okay, now we want to find all side lengths and all angles. So the first thing we need to do is solve for our side lengths because we're able to do that without any problem because we know how to find the distance between two lines on a coordinate plane. You have two options. You can either use the distance formula or you can use the Pythagorean theorem. For this situation, I'm just going to use the Pythagorean theorem. So I'm going to create right triangles with each of those sides. So I went over 1, 2, 3, 4 here, and I went up 1, 2, 3 spaces there. So I'm going to have a squared plus b squared equals c squared, which will be the side AC. So I'm actually going to write it like that too. So I have 3 squared, or 4 squared, plus 3 squared is equal to AC squared. 4 squared is 16, 3 squared is 9, 16 plus 9 is 25, so I have 25 is equal to AC squared. We're going to take the square root of both of those sides, which means that AC is equal to 5. Now I'm going to do that again for sides BC. We have 1 and 2, so I have 1 squared plus 2 squared is equal to BC squared. 1 squared plus 2 squared equals BC squared. 1 squared is 1, 2 squared is 4, so I have 5 is equal to BC squared. I'm going to square root both of those, which means that BC is approximately equal to 2.24. All right, last but not least, I have side AB. I'm going to type that in after. I'm going to check Right, next we have side AB, and we go up 1, 2, 3, 4 squares, and over 2 squares. So I have 2 squared plus 4 squared is equal to BA squared. 4 squared is 4. 4 squared is 16. 4 plus 16 is 20. So I have 20 is equal to BA squared. We're going to take the square root of both of those sides, and that leaves me with BA is approximately equal to 4.47. Okay, those are my side lengths, which I was solving for. Now that I have my side lengths, I need to solve for my angle measures. And I actually think it'll be helpful if I label those. So we have 5, we have 2.24, and we have 4.47. Now we're going to use trig functions to solve for our missing angles. So I have angle A and I have angle C that I need to solve for because I already know angle B is 90 degrees. Let's start with angle A. So angle A in relation to these other angles is opposite from 2.24, adjacent to 4.47, and 5 is the hypotenuse. I'm just going to choose to use cosine, and I am looking for the angle, so this will be the inverse cosine function. So to find angle A, what we will have is the inverse cosine of the adjacent, which is 4.47, over the hypotenuse, which is 5. We're going to take that and we're going to plug that right into our calculator, and when we do so, that gives me that angle A is approximately equal to 26.62 degrees. All right, now that we have one angle measure, we can use that to solve for the other angle measure here, because we know that there has to be 180 degrees in a triangle, so you can simply subtract it from 180, and including this 90 degree angle, of course. However, we're focusing on using our trigonometric ratios, so I'm going to use another trigonometric ratio for this angle here. So angle C, if I choose to use those same two sides, will be opposite from 4.47, and then 5 is still the hypotenuse. So if I'm looking for opposite in the hypotenuse, I have to be using sine. But again, we're solving for the angle, not the ratio. So if we're solving for the angle, we have to use the inverse sine. So what I have is angle C is equal to the inverse sine of 4.47, which is opposite, over the hypotenuse, which is 5. We're going to plug that in our calculator, which I already did, and that gives me angle C is approximately equal to 63.38 degrees. And that is how we were able to find all three sides and both of our missing angles for this whole triangle. Now we do technically need to write down that angle B is equal to 90 degrees as well, because that is one of your answers, but it is something that we already knew. So example 2 works the same way, except we don't have a coordinate plane. So example 2, we're going to talk about what do you do if you need to find all side lengths and angles of a triangle with these coordinates, but you don't have a graph. The first thing that I'm going to do is I'm going to draw an approximate for my graph. So I'm not actually going to plot any of these points. I'm just going to draw a coordinate plane, kind of, just like this. And then I have a point -3, -2, which could be around there, -3, 5, so that's straight up and positive, that will be my B. And then 6, -2, which is going to be level with point A, but in the positive, and that's C. So this is not a perfect drawing. It's not to scale at all, but it gets the point across. So if I don't have my coordinate plane, then using the Pythagorean theorem is a little more difficult than the distance formula. So this time we're going to use the distance formula. So this time we're going to use the distance formula. So my point A is -3, -2, and my point B is -3, 5. In my distance formula, that is the square root of x1 minus x2 squared plus y1 minus y2 squared. So what that looks like for us, that would be AB is equal to the square root of my x's, subtracting each other. So A was -3, B was -3, so I have -3 minus -3 squared plus my y's, -2 and 5, -2 minus 5 squared. That's all under that radical symbol. And this needs to go in the same order. So if this is from point A and this is from point B, then the second set here also has to be A and B. So if we think through this, negative minusing a negative is the same as a positive. So that's -3 plus 3, which is 0. So I really only have -2 minus 5. -2 minus 5 is -7. So I have -7 squared, which is 49. So this is equal to the square root of 49, which means that AB has to be equal to 7 because the square root of 49 is 7. So that's one side length, and I'm going to mark that down over here. Next, I'm going to solve for AC. So AC will be equal to the square root of, I already know my x and y from my A, so -3 minus something squared plus -2 minus something squared. Now I need my x and y from AC, for C, sorry. So my x for C is 6, my y is -2. So I'm going to plug that in, 6 in the x place and -2 in the y's place. Over here we have -2 minus a -2, that's going to cancel out and give me 0. -3 minus 6 is equal to -9, so this is really equal to the square root of -9 squared, which is 81, which means that AC has to be equal to +9. So we have the square root of 81 is 9, that's AC over here. Now the only thing that's left is to solve for our hypotenuse, which will be BC. So BC is then equal to the square root of my B's minus my C's. X's first, then Y's. So I have -3 minus 6 squared plus we have 5 minus -2 squared. -3 minus 6 is equal to -9, so that is 9 squared, -9 squared, which is 81, plus 5 minus -2 is the same as 5 plus 2, that's 7. 7 squared is 49. So I have the square root of 81 plus 49, which when we calculate that out, gives me approximately 11.4. BC is approximately equal to 11.4. We'll put that down over here as well. All right, so now that we have all three sides, we know that this angle is 90 degrees. It has to be the 90-degree angle. So we're going to write that down first. That angle A is equal to 91 degrees. We'll change colors for this here. So angle A equals 90 degrees. We still need B and C. We need to use a trig function to find it. So I have, let's just start with angle B. Angle B, we have all three sides, so any function will work. I'm just going to use cosine just because. So I have the adjacent side of 7 and the hypotenuse of 11.4. Again, we're solving for the angle, so we're using an inverse function. So angle B is equal to the inverse cosine of 7 over 11.4. When we plug that in our calculator, that gives us that angle B is approximately equal to 52.12 degrees. And then we also have angle C to solve for. I'm just going to use those same side measures. So I have 7 and 11.4. This time 7 is opposite, so we're going to be using the inverse sign. So angle C is equal to the inverse sine of 7 over 11.4. When we plug that in our calculator, that gives me that angle C is approximately equal to 37.88 degrees. All right, so there is all three of our side lengths and all three of our angles. All right, this is where we're going to stop for today. We'll continue on with our video lessons in Unit 10, covering two-dimensional geometry.